So if I want to continue that introduction a little bit further and introduce myself a little bit informally, I would say that I'm kind of a very busy person, having a lot of things in my plate at the same time. So to kind of manage that busyness, I started, organizing my tasks ahead of time. So I generally make like my daily schedules like this, and then that generally starts with some physical activity, going to gym, doing some activities. Then I have to go to school, teaching to some computer science students, and after that I have to go run some errands, around the town. Probably go to bank, transfer millions of dollars from here to there, and then some other errands, probably visiting doctor, going for some shopping, and sometimes I have to go back to school to meet with my graduate students, analyze whatever they have done over the past week, then meeting with colleagues and plan for doing nothing in our department, and then eventually I have to go home and pick up kids from school. So this all makes me generally like this. So you find me generally in this situation and mood. So to avoid that, I thought that I have to do something, right? So I consulted with my wife, and we concluded that we have to drop some of the activities, right? So dropping these will probably make me some more happy person like this, and probably a little bit more successful. In addition to that, the remaining tasks in my daily schedule probably would be done in a better quality, in a better way, or get more chance to be done. So this was the idea in my life. Then I thought, and it is working. I hope it works. I don't know yet. So then I thought probably I can apply this to my research too. So let's see how I can apply this idea in my research. And by the way, if you get the idea of this kind of funny example, you got the main idea of this paper and this work. However, I should note that as British people say, the devil is in the detail, right? So there are still further details coming up. So the title of our paper is in fact Robust Dynamic Resource Allocation via Probabilistic Task Pruning in Heterogeneous Computing Systems, Scaling, right? So, but this is a formal name, and I don't like formalities so much. So if you really ask me what the title of this paper is, The Art of Saying No. So this is the real title of this paper, and this is the result of work of my former student James Jeffrey, Chavi Deminar, who accompanies me in this conference, and myself. And they are from University of Louisiana. Okay, so let's start by setting the stage and provide some definitions. So all of us, I guess, in these 2 days of the conference are convinced that heterogeneous computing is important and is going to become even more important. So different types of processors are coming along, accelerators, FPGA, different forms of, processors, GPUs, different forms are coming along. Along the same line, clouds do provide different types of services like CPU optimized GPUs, IO optimized. So a wide variety of them are in the market. What we concluded is that the current heterogeneous computing systems are of two types. They are either consistently heterogeneous or inconsistently heterogeneous. By that consistently heterogeneous, we mean like a situation like this, that in which some machines are consistently better than others, right? Machine B is faster than machine A. However, in inconsistent heterogeneity, which is actually more exciting, and that's what we are more concerned about in the coming years or even now, is inconsistent machine heterogeneity, in which some tasks are good for some specific purposes. I guess the examples are evident, like GPUs are good for graphical processing, CPUs are good for memory-intensive applications, and so on and so forth. Okay, sorry, I thought there was a question. Okay, so we not only have heterogeneity on the machine side, but also we have heterogeneity on the application side. So let's consider the live video streaming as a motivational example. So in live video streaming, we have publishers all around the world have like starting publishing contents, live contents, right, in different formats using different devices. And that is done generally through some what is so-called streaming engine, live streaming engines. Nowadays we have a lot of them: YouTube Live, Facebook Live, Instagram Live, very, very popular nowadays, and many others. So what they do is getting this content, process them, and stream them to a wide variety of display devices, right, from big screens to mobile phones and stuff. So, what do we learn from this motivation? First, we learn that in this motivational example, liveness is important, right? So it is important to be live. I don't want to watch something happen 10 minutes ago. I want to see what something happened 1 second or 1 millisecond ago, probably. In this example, in this type of application, tasks have hard deadline. There is no point in processing a task that has happened like processing a segment of video that has happened 5 minutes ago. I want things live. Therefore, the tasks that are useless can be dropped, right? So task dropping is a big thing. Also, as I said, we have task heterogeneity. And here, really, in this example, task means video segment being processed. For example, some needs to be changed in the compression format, some needs to be changed in the resolution format, and so on and so forth. So kind of different types of tasks, or what is so-called task types. So that's another thing that we have in this side. And as I said, we have an inconsistent heterogeneous system, like a combination of GPUs, CPUs, and so on and so forth. So this is kind of the setting the stage and introducing the basics of this work. So now let's go one step deeper and talk about the system model and the details of what we consider in this work. So the thing is that the execution time of the tasks, of these tasks that we introduced on heterogeneous machines, or even actually on each machine, is a stochastic, right? I mean, the source of stochasticity is like that's a different story, but simplest things in this example, we can say that different video segments have different sizes, right? And that is the source of uncertainty. In other words, changing the resolution of a segment is not always taking, let's say, 2 milliseconds. It's not always like that. It's a stochastic, but it's uncertain. Well, there are ways to capture this uncertainty. One way being using what is called as PMFs, probability mass functions, which essentially is something like that. What it shows is that, for example, a given task takes 2 seconds. I'm just saying hypothetically, with 0.2, with the probability of 0.2, 3 seconds, with 0.4, and so on and so forth. So this way we can capture the stochasticity, right? And we call it as execution time PMF. Well, this is for one task. In an inconsistent heterogeneous system, in fact, what we have is a system like this, and what we have to maintain, the scheduler or the mapper needs to maintain, is what we call it PET matrix, which is probabilistic execution time. Basically, each entry of this matrix is one of those PMFs that I showed in the previous slide. So with that in mind, the goal of this research is to overcome that stochasticity, is to make the system robust against that stochasticity exists in execution time of the tasks. What do we mean by robustness? The exact definition of the robustness, I just read from the slide. Robustness is the degree a system can perform correctly in the presence of uncertainty. So I guess it's clear what is uncertainty, and perform correctly means keep the performance, right? And what is our performance? How do we exactly define performance in our system? We define it as the percentage of tasks that can meet their deadline on time. In the example we provided, segments needs to be processed on time. Yeah, before the deadline. And then the approach that we propose to achieve that robustness, to maximizing that percentage of tasks that meet their deadline, is to prune tasks. So we propose a method to prune hopeless tasks, the tasks that are unlikely to succeed. More specifically speaking, the contributions of this work would be first focusing on task dropping. So pruning and dropping are pretty much similar. So when we do drop tasks, the dropping impacts the execution time of the remaining tasks, right? So there is no model to tell us what is that impact. So we need to do that. And then, of course, then once we do that, modeling the dropping, we need to we will explain the task pruning mechanism. That's the mechanism that we propose, and eventually we propose some mapping heuristic working based on that mechanism. We call it PAM, pruning aware mapping heuristic. Okay, so first challenge, the impact of dropping. How is the impact of dropping? How to model that? To explain that, I need a little bit of recap from statistics. So if we know the distribution of two random variables, x and y, then the question is, what is the distribution of z equal x plus y? Any idea very quick? Okay. The answer is using convolution, right? So if we convolve the PMFs of those two random variables, then the resulting distribution is the sum of those, in fact x plus y, or the distribution of z. So let's give and there's a formula for that. There's a known formula, nothing specific about that. Just a very quick example. Suppose that z is the distribution of sum of rolling a dice 2 times, right? So that 2 times means our x and y random variables. So the distribution would be, the PMFs would be something like this. For example, with some probability we get the sum value 6, with some probability we get the sum value 7, and so on and so forth, as we get 12. The values can be, because best case you get 2, 6, right? Okay, so now let's go back to the heterogeneous computing world and map that concept in our context. So suppose that we have a core, or what we call it, a machine, and a local queue for it. So the core is running a task, right? And then there is a local queue. Some tasks are queued in that local queue, and there is an arriving task. So the purpose is to calculate the probability of, the completion time PMF of this arriving task. That's my goal at this point. So for that purpose, based on what I just explained, I need to convolve the PMF of this running task, the remaining PMF, to be very specific, the remaining PMF of it, with the execution time PMF of this green task, and then eventually with the execution time PMF of the silver task, right? So that will give me the completion time PMF of this black task, arriving task. And this is the formula for that. It's pretty much, or in fact exactly the previous formula, but kind of customized for this context. Okay, this is good. This is called stochastic completion time for an arriving task. This is good, but this does not support dropping, right? How about if a task gets dropped? How does these PMFs will change, right? So that's the thing that we have solved in this paper, and this is the mathematical model that we provided for that purpose. This gives us the completion time PMF in the presence of task dropping. Well, I'm not going to overwhelm you with so much math. I've been exposed since this morning or probably yesterday to so much math, so I'm not going to overwhelm you with that. Instead, I'm going to give you some intuitive examples. So let's assume that we have an arriving task I with deadline 7. Okay, this is the arriving task, that black task. Okay, and then to obtain its completion time PMF, we have to convolve it with the completion time of the PMF of the tasks behind it, that green one, right? So suppose that this is the completion time PMF of task I-1, the one ahead of it, right? So note that the deadline is 7, right? Because the deadline is 7 if the result of convolution, okay, oh, sorry, if the previous task, the execution time of the previous task, goes anywhere in this impulse or anywhere later than that, this task will not be executed. This will be dropped, right? Therefore, drop means what? Drop means the execution time will be 0, right? So therefore, for these impulses, the execution time of this one will be 0. Therefore, we exclude this from the convolution because they will not, for these values, this will not be executed. Okay, so these are excluded. So then we do the convolution, and then this is the result of convolution. Sorry, this is the result of convolution. And we noted at the end that the deadline is 7. So these values are not going to happen. If it runs to this impulse or this impulse, it will not happen, right? If it runs to those impulses, the task will be dropped at the impulse 7 because that's the deadline. You are not allowed to run beyond the deadline. So these impulses are aggregated to the seventh impulse. Okay, so we are pretty much done. Just one thing, we excluded this impulse. What will happen to them? They may still happen because this task I-1 may run to 7, 8, 9. Right? So in fact, once we are done, we apply them again on the completion time of this task I. Because if they run, the execution time of this one would be 0. So in fact, these are added by 0. So 7 will be added with 0.3 and so on and so forth. Okay, I know it is difficult. It took a while for us to understand, and I cannot probably do a good job of explaining that in few seconds or minutes. But anyway, this is the completion time PMF of task I in presence of task dropping. And then this example, this intuitive example is the crux of this mathematical model. Okay, so anyways, we could get the completion time PMF of task I, right? So how can we use it? The use of that completion time PMF would be in calculating the probability of success for task I. So using that, we can calculate the probability of success for task I. This is that completion time PMF from previous slide. Let's assume that the deadline is somewhere around here, 7.5. Okay, just hypothetically. Therefore, the chance of this task meeting its deadline are the sum of all impulses before the deadline. Right? So therefore, I just need to sum them up, and then this is the formula, which is essentially not too difficult. It's like the probability of task I on machine J, because it is heterogeneous on machine J, and then sum of all the impulses. Each Cij means one impulse that are less than delta, which is delta. So this is the probability. So we could obtain the probability of a task meeting its deadline. Now, we can leverage this probability for our pruning mechanism. Let's see how. So essentially, why to prune tasks? I should ask this question first. The reason is that there is no benefit in processing low chance tasks. Processing low chance tasks or hopeless tasks just adds to your cost. No benefit, and even worse, it causes delay for the remaining tasks. So if you overwhelm your daily schedule, even your essential tasks will be delayed, right? So that is for these reasons we need to do the pruning. And also pruning helps with coping with the oversubscription of the system. If your system is oversubscribed and for whatever reason you cannot stretch it, then this solution is good to get rid of that oversubscription a little bit. Okay, so now let's see how that pruning mechanism works. So this is our heterogeneous system with a batch of arrival tasks and a batch of local queues of assigned tasks, and we have a mapper here with the scheduler, right? So our pruning mechanism works in consultation with the PET matrix that I introduced earlier. So what it does, it applies dropping to the machine queues, to the machine queue means local queue, to the local queue, drops the tasks that are unlikely to succeed. It also has another way of operation, which we call it deferring. So for those tasks that have not been mapped yet, they are deferred. So this basically constructs our pruning mechanism. So our pruning mechanism, in short, is deferring plus dropping. That's what it is. So more specifically, on every mapping event, our mechanism, on every mapping event, it applies deferring. So deferring is always good to it. Why to defer? Because the system is heterogeneous and the tasks have affinity with machines. So for example, if there is a graphical task, it is better to be assigned to a GPU, hypothetically, right? So this is called affinity. So if the GPU is busy at this scheduling round, maybe at the next scheduling round we get the chance to assign it to this graphical task, right? So therefore deferring can be useful. Task with chance of success is below a deferring threshold or deferred to the next mapping event with the hope that it will get a better chance of success. So why do we drop? Or when do we drop? We do dropping only when the system is oversubscribed. Dropping is not a great thing to do, right? We just do it when we have to. So basically tasks whose chance of success are low will be dropped, and then the dropping will increase the chance of remaining tasks. That is a very important factor. Another important factor that is generally ignored is that dropping tasks will not only improve the chance of remaining tasks, but also reduces the compound uncertainty. So we have compound uncertainty, then we have less distribution to convert, the compound uncertainty would be less. So that's another advantage of dropping. So let's say a very quick example. I do not have so much time. So let's say the threshold, the dropping threshold is 5%. Okay, and this is our scheduling queue, our local queue. So starting from the head of the queue, this is good enough. We can keep it. This one is below the threshold, so it has to be dropped. So when we drop it, then of course the ones that are behind, that was very low chance, now gets a much better chance, and so on. And it reduces the uncertainty. I could not show it in this example, but I hope you understand that the uncertainty, compound uncertainty, would also reduce. Okay, so basically, what is task deferring? I guess I explained this already, but I would like to mention it again, that in fact, deferring is the art of saying not now. So when you schedule your daily tasks, similarly in the heterogeneous computing system, always think of, if you are very busy, always say, maybe not now, maybe now is not a good time, maybe later, right? The art of saying not now. Why? Because specifically in a heterogeneous computing system, we have that affinity issue, and if you postpone things to the next mapping event, you may get a better affinity. I introduced what does affinity mean. Okay, deferring can raise the chance of success for a task. Okay. Are we done with pruning? Almost, but we still need to answer some questions. So the first and foremost question is that, okay, I was always talking about like dropping and deferring thresholds. What are these thresholds? Who set them, right? How to set them? So that's one question that needs to be addressed. So, and when to begin and cease dropping. So that's another question that needs to be addressed. When the system is oversubscribed, I already addressed this question basically. And then this pruning mechanism is prone to unfairness because the system may, eventually drop the difficult tasks and just keep the easier tasks to maintain the robustness. So it is prone to unfairness. So to address all these questions, we propose this pruning mechanism. It has several components. So this pruning configuration that in fact includes the dropping and deferring thresholds. This toggle component is in charge of understanding the oversubscription and switching to the aggressive mode, basically dropping. And this fairness module is in charge of applying fairness, making sure that the tasks, making sure not just easy tasks are being processed. Okay, so about determining the threshold, that is the one that I want to elaborate a little bit on. Basically, the thresholds that we want to define, we thought that it should not be a system-wide threshold, dropping threshold. It has to be task level. It has to be individualized. Why? Because look at this example. So, or maybe let me give you a more intuitive example. In your daily schedule, it doesn't matter if you drop the very last task. That doesn't help you. The one that very beginning helps you if you drop it, because everything else will be pushed forward, right? So therefore, that shows us that the position of the task is important to be considered for dropping. So another factor that we realize at the task level helps in determining the dropping threshold is the skewness of the PMF. So about the skewness, basically the distribution, the completion time can be left skewed or right skewed. Right? So this is a right skewed. Both have like 75% chance, but this is left skewed and this is right skewed. So, but they give the equal chance. But in fact, this is a better option for dropping. Why? Because it's like, for example, you have scheduled a meeting for 1 hour, okay? But when you want to go to the meeting, you say to yourself, I think it's not going to take a lot of time. So it means that you are more biased with these impulses. All right. So that's another indication that we should care about, skewness in the task level dropping threshold. And I have to skip this slide. This is how we determine the mathematics of how we determine the dropping threshold. And here, in this experiment, we determine, and one more thing, the differing threshold has to be always more than the dropping threshold. Because otherwise, what would happen is that you assign a task that otherwise will be dropped instantly. And in this experiment, we show that basically what is the impact of dropping threshold and the different threshold, how it can be inferred from that dropping threshold. This experiment shows the impact of our pruning method over different arrival rates. And we can see that in both cases, we achieve a much better robustness in compared to the for example, heuristic like mean and similar heuristics. And this one shows the cost, how much cost benefit you can gain in systems like cloud-based systems. I have to skip this. And then in conclusion, I'm done. So the conclusion very quick is that pruning is effective in increasing the robustness. You always benefit from thinking of deferring. So defer should be always applied. And so this is a good lesson for the life, right? So always thinking of doing things later. And then dropping is also effective, but mainly when the system is oversubscribed. So therefore,